We'll begin with a presentation of CEDA by its president, Miguel Silveira, and then we will get on to the keynote from Helen Lee. So, Miguel.
Thank you very much, Ian. Welcome, everyone. Thank you for coming over to this CEDA keynote luncheon. My name is Miguel Silveira. I'm the current president of the IEEE Council on Electronic Design Automation. CEDA was formed in 2005, so we'll be 20 years next year. So expect next year there'll be celebrations. I hope you are here. We're starting to make plans for celebrations throughout the year on the various activities that we organize and we held. The field of interest of CEDA, as you might expect, is anything that is related to the design automation of circuits and systems. This includes tools for automating the designs, for analyzing designs, verifying and optimizing. And the goal, of course, is to be the leading provider throughout all of IEEE and the home for the community that does design automation. This is why our member societies, as you can see, cover a wide spectrum of interests in electric and electronic engineering in IEEE. So we manage, as for those that were earlier today in the opening ceremony, you heard George Gillen mention that we manage several types of activities. One that is very obvious are conferences, which we sponsor and organize, DATE, DAC, ICCAT, several others. There's too many to put in here. These are sort of the flagship conferences. And there are lots of opportunities in here for those that may consider organizing a conference, a symposium, or a workshop. Please get in touch with us, and if the topic falls within the interests of the Council on EDA, we'll be very happy to help you organize it. We can do this also in the context of chapters, which we have throughout the world, and we're also open to the possibility of you opening chapters in your own regions and your own countries. Again, come and talk to us. Besides conference, we also sponsor and manage publications. Several of them are shown here, the transactions on computer-aided design, embedded systems, letters, etc. We're also a participant on a new journal coming up, which is the Transactions on Circuits and Systems for Artificial Intelligence, a new journal for which we are very optimistic will be a very interesting outlet for research in our area, and which will start later this year. We also organize several awards. You saw today that Ian, my co-chair, received the Service Award. There are other awards, the COO Award for Young Professionals, the Kaufman Award, which is sort of the Nobel Prize in our area, and we have some recipients here that I can see. Nani is here, and I'm sure there are others in the audience. The Best Paper Awards at conferences and Best Paper Awards also in journals. We also have a Distinguished Lecturers Program, and you can get in touch with us to try and get one of our distinguished lecturers to come and visit you or to give you an online presentation on a topic of your choice. We do have also a student travel grant program that students can apply. We feel that this is not sufficiently known to many of the students, so if you are a student, you should now be aware that we have this program that provides financial support for those in need that have a paper in one of our conferences to come and present it. So the conference, the council, as you can see, has many possibilities of supporting your activities, and this is why we exist, to organize, to manage, to support, and to provide also some experience for those that are starting in our field. So there are lots of ways of getting involved in the Council of EDA. Many of them are shown here, and I've talked about several of them. So don't be shy, come and talk to us, and join the Council. By the way, if you're not an IEEE member, you should be. And if you are an IEEE member, you can become a member of the Council for free. So you just have to tick it when you do the registration. And you should do that because then you get access to more information. Thank you very much. I'll give it back to Ian. Thank you.
Great. Thanks very much, Miguel. So it's my pleasure now to introduce our distinguished lecturer from CEDA for the lunchtime keynote, who is Professor Helen Lee. She is the Clare Boothe Luce Professor of Electrical and Computer Engineering at Duke University. She has degrees from Tsinghua University and Purdue University, and she served as associate editor on multiple IEEE and ACM journals and was general or technical program chair of more than 30 international conferences. She has received multiple career and research awards, including 9 Best Paper Awards and other nominations. Her research interests focus on neuromorphic computing systems, deep learning acceleration and security, memory design and architecture, and high performance and energy efficient computing. And she is a fellow of both IEEE and ACM, and she has come here to talk to us today about AI models for edge computing, hardware-aware optimizations for efficiency. So I will just bring up
Thanks, Ian.
the presentation.
Thank you.
The floor is yours.
Thank you. Good afternoon. Thank you, Ian, for a very kind introduction. I also wanted to thank CEDA for inviting me here and talking about my research. In fact, this is my first time to be in Valencia, perhaps so as to many of you here. It's a very beautiful city. I'm very looking forward to exploring it more in the following days. So today, I'm here to talk about our research on AI models for edge computing, hardware-aware optimization for efficiency. Well, as we all know that we are now in the era of big AI. So the chart over here summarizes the AI model changes over years, measured by the number of the parameters and they use. And as you can see, the number of the parameters increased very fast, especially in the recent years, right? This is merely because of the success of a large language model. So years ago, we may say that an early language model like BERT base with 150 or 110 parameters, we may run that on mobile devices. Now what we have, GPT models. GPT-3 has 175 billion parameters. So definitely, we need very powerful server in order to run the model. We're also talking about having AI at edge devices. So what's the expectation on edge devices? Small, lightweight, and efficient. So here, we compare the AI model trend versus the change of hardwares at edge devices. Okay. The left here actually compares the model size versus the memory capacity of typical mobile devices. And the right-hand side compares the expected inference computing speed versus the maximum throughput can provide by these physical devices. Despite significant innovation at hardware levels, we still can say that edge devices have failed to keep up the rapid growth of AI models. What can we do? Certainly, a holistic approach to combine the algorithm level and the hardware level is essential. So in this conference at date, I guess many things has been discussed about the hardware innovation, the integrations in between the software and hardware. Our group has been concentrating on this research thread. So today, I will majorly talking about our efforts on AI model optimization by considering the hardware constraints during this process. So take, for instance, a neural network shown over here. A typical approach to simplify or optimize the DNN models include simplify the topology through pruning techniques, or we can streamline the operations and through quantization techniques. Okay. So in the following, I will elaborate a little bit more on how we optimize for efficiency during pruning and quantization. So I will start with the pruning first. Okay. So the basic concept of pruning is involving removing the redundant of parameters. Okay. So for example, considering the weight parameter, which is in 0. The weighting or summation results are known without having the actual computations. Okay. And then the benefit of pruning are twofold. First, omitting the storage of 0 values can help us save memory storage. And the second, if we're skipping the computation related to 0-valued parameters, and then we can reduce the execution time and the associated computation energy consumption. So both sides, as you can see, that then we can help to reduce the resource usage and improve the efficiency. One thing we noticed, in fact, is that the concept of pruning is not new. The idea was proposed at least in 1989 by Professor Yang LeCun. So in NeurIPS at that year, Professor Yang LeCun published a paper called Optimal Brain Damage. And he discovered that up to 60% of the parameters can be removed without affecting the mean square errors. Well, the interesting part in this work is the step 3 over here require calculation second derivatives, which is still very costly even nowadays. Well, what do we do when we're talking about the pruning? Okay. The objective is to find a set of the weight parameter, theta here. The goal is to achieve optimal performance, for example, in accuracy. Meanwhile, to minimize the number of non-zero parameters. So L0 norm mathematically quantifies the number of non-zero parameters in a matrix or a vector. Therefore, a formal objective can be formed as to minimize the L0 norm while ensuring the loss function can satisfy a preset threshold, such as an epsilon over here. Well, let's look at the L0 norm functionalities. L0 norm is combinatorial in nature, which is pretty nice. However, while we applying that for optimization, we find it's challenging. So as we illustrate over here, So as we illustrate over here, here is the 2D contour maps for L0 norm and its first derivatives. The two maps shows that first, L0 norm is not continuous, and the second, it is not differentiable. What does it mean that this function is not suitable for gradient-based optimization method? So alternatively, people adopt the L1 norm or called lasso regularizers. It can provide a continuous sparsity-inducing regularization. Well, what is L1 norm? Essentially, it is the summation of absolute values of weight parameters. And when we observing its derivative with respect to and specific weight parameters, it's either to be the sign of Wi here if Wi is non-zero, or it's 0 if Wi is 0. So as you can see, L1 norm is continuous and differentiable, made it more suitable for gradient-based optimization. Also, I show the 2D contour maps here for L1 norm and its first derivative. The chart actually indicate that an L1 norm always shrink the non-zero weight elements at a constant speed until they all reach to 0. And this is how it was named as a LASSO, least absolute shrinkage and selection operator. Well, so far, I'm mainly talking about the indication at algorithm level. How about at a hardware level? Again, take a look at the dense neural network here. It can be translated into a weight matrix. So in this illustration, what I have is arranged input neurons along the horizontal directions, and then the output neuron is calculated and collected along the vertical direction. At each interaction, there's a weight parameter. While we're doing specification on the weight matrices, as illustrated on the right-hand side, and part of the weight and the neurons will be pruned. So some of the weight parameters are highlighted by the gray color to signify the 0. Okay? And if an output neuron is removed, the associated weight along the vertical directions and can be 0 out. Well, how modern processors to handle specifications? For instance, and let's look at the crossbar-based and DNN accelerators. Assuming there is a very large weight matrix, it will be partitioned into many smaller ones, each loaded and computed on one crossbar-based processing engine. Okay. Well, without any optimization, the same techniques will be applied to the sparse matrix as well. In other words, the specification at algorithm level will not automatically lead to the saving at hardware execution. So when we observe this, and a simple idea comes to mind, why can't we reorder and the input and output neurons to extract some dense blocks? And this inspired our very early work on clustering the sparse neural network. In this work, our assumption was obtain a sparse neural network at the algorithm level first, and then can we optimize the hardware implementation? So more specifically, what we did was performing spectral clustering in non-zero neurons. And the process was pretty simple. It's just reordering the input and output. Through the process, and we could build in certain dense blocks, and then we can extract it. And then for the remaining, so we continue extracting or reorganizing and extracting the dense blocks until all these dense blocks are executed on crossbar arrays. And then there are a few outliers remain and can be handled individually. More specifically, through the process, and what we do is do clustering the connections, and then resizing those dense blocks and depending on the available crossbar arrays, and then extract them, and then repeat that. Through the process, actually, we significantly reduce the number of crossbar arrays required for the computation, and improve the hardware execution. Well, let me reiterate what we did for this work was starting with a sparse neural network obtained at algorithm level, and the optimization was primarily on crossbar-based and DNN accelerators. So while we are doing this, and we were also curious in how is the performance on traditional platforms. And very interestingly, about 10 years ago, we tried this experiment. This is an AlexNet, sparse AlexNet on ImageNet data set. And here we show the experiments on CPU and GPUs by layers, like convolutional layer 1 to 5. If you observe the purple curve, you can see the sparsity level are all very high. For example, convolutional layers, about 90% of the weight parameters can be zero out. Well, when we really observing the performance on hardware, the speed up is very marginal. And in fact, then some layers like convolutional 1 and 2, they suffer from performance degradation. The problem arises then from the random distribution of those non-zero elements. So over here, I give some example. This is a convolutional 1 layer. The black dot indicate non-zero weight, and the black indicating those are zeros. So as you can see, the distribution of non-zero parameters are pretty random without any pattern. So how can we help to improve the hardware implementation? We can definitely use the clustering ideas that I just discussed, or through some encoding and decoding schemes available on the CPU and the GPUs. But you can imagine, no matter what, it involves either software or hardware overhead. As a counterpart, structure sparsity refers to the situation that we tend to zero out the elements along the entire row or entire column, like what I illustrate on the right-hand side. So the compression can be realized in a much simpler way. For instance, we just number the row numbers or column index and made it very compact. The question then is, and how can we achieve that? In fact, then, we propose to apply lasso in a structured way. Recall, we talk about the L1 norm. What does L1 norm did is to shrink uniform in each directions. In fact, then people also tend to apply L2 norm, and its functionality is to shrink toward the region. Like means that all the dimensions are set to 0. So what we proposed is to apply L1 regularizer to the L2 norm of the target groups. For instance, imagine this is a weight matrix array. And imagine we arrange the groups by identical input neurons, like along the horizontal directions. So in this case, and we first apply L2 norm for each groups, and then apply L1 norm across all the groups. It's a very simple approach. And in the broader context, and what we can do, or our understanding is, and the grouping the parameters depends on the desired level of granularities of the pruning. So when we're talking about the convolutional neural networks, and for instance, the user can define by itself, and so the group can be filters, can be channels, can be any shapes, or even the entire layers. So you pick. Okay. So again, once you decide, we can apply the group lasso to the grouped parameter. I don't show a lot of results over here. All the results in here, in fact, was published back to 2016. So here is a simple comparison again on AlexNet. And then while we compare is in applying L1 norm versus in structure sparsity learning SSL, what we proposed. Accuracy level-wise, and they are similar to each other. But if you're looking at the sparsity level, obviously our method then shows overall sparsity is lower. However, we obtain a much higher speed up. So since then, this method has been studied and integrated into or supported by many leading commercial deep learning products. Afterwards, we actually further studied and proposed what we call the deep Poier. The idea is to use the square root of the L1 norm versus an L2 norm ratio as the regularizer. Okay. So the chart over here is a selection of a random 100 weight parameters and show they're evolving through the training iterations. And as you can see, the deep Heuer achieve what we call the auto-trimming effect, meaning we tend to remove the weight parameters in small values, but maintain the weight parameters in large values. And the black dashed line over here represent the threshold for parameter protection. The method of structure pruning can also be applied to other structures. And for example, we are able to apply that to long short-term memory. In fact, we also studied how to remove some hidden layers and by combining with structure pruning techniques. And this method has been applied to Intel Gaussian and Neural Accelerator GNA. In this hardware designs, and they fetch the weights in chunks of 16 bytes, and we naturally take this 16-byte trunk as the group and do the structure pruning. All right, so far I'm talking about the pruning techniques. And as I mentioned earlier, another optimization scheme is called quantization. The goal is to simplify the operations. Again, the idea of the quantization is also very simple. Its principle is to reduce the data precision representations. For example, if we can start with the floating point 32 and downgrade that to integer 32, integer 8, integer 4, and as you can see, with such simplifications, the required hardware complexity can be reduced tremendously. In addition, when we reduce the bits representations, the associated memory can be reduced, and the execution speed can be improved. Our own research on specifications stemmed from another branch of my research on neuromorphic computing. The idea of neuromorphic computing is to mimic human brain structure and to rebuild computer architecture for extremely low power consumption, for very high parallelism execution, and for cognitive computing. And IBM True North was taking as an advanced neuromorphic platform at the time. And in this design, in fact, the weight parameters are realized by SRAM. And therefore, we must use 0, positive and negative 1, and positive and negative 2, such kind of digital numbers to represent it. So the question then is, with such high-level simplifications, the performance of an IBM True North might not satisfy the requirement. So at the time, the proposal or the solution was to provide multiple duplicated copies and also extend the input and output spiking trend in order to improve accuracy. So let me explain this a little bit. The left-hand side over here actually shows the training scheme we call the T-learning. Okay. Through the learning processes, as you can see, the input and output activations are represented by spike probabilities. And the weight parameters, and we call connectivities, also can be trained with the real value representing the connectivity probabilities. Okay, so how can we map to the hardware for execution? We wanted to increase the instances in spatial and the temporal domains. Okay, how can we increase the instance in spatial domains? The way is to produce a few copies, and for each copy, the connectivity here is sampled based on the connectivity probability. So imagine if you have 5 copies, and your probability is 0.8, possibly 4 copies, and they have value of 1, and 1 copy, there's a value of 0.2. So statistically, it's representing 0.8. This is how we duplicate that in the spatial domains. And of course, in the temporal domains, it's come with the spiking trains at input activation and output activations. And so we could use 5 pulses or 100 pulses to represent these numbers. So when we're looking at this in schemes, and we were wondering, like, what is the variance of the outputs? And obviously, it highly depends on the variance of the input and also weight parameter. And particularly, what we find is, for the weight parameters, and when the weight close to 1 and the zeros, the variance is low. While when it's close to 0.5, it has the highest variance. So we propose in this penalty function, regularizer accordingly, and apply highest penalties at 0.5. Our results shows that before applying the penalty, if you're looking at the weight form here, the weight distributions are kind of uniformly, but a little bit more at 1 and 0. Well, after applying the penalties and the weight parameters, and since you clustered toward the 2 side with very minimal numbers and in the middle, what is the impact on our side? So, in fact, with all these, we can reduce the duplication. Again, in temporal domains and the spatial domains. The left figure shows, like, in order to maintain the similar accuracies, and we can reduce the spike per frames 6.5 times. And on the right-hand side, and it shows the use of the cores and can be dramatically reduced as well. Okay, so this is how we can improve the execution efficiency for like a true north situation. In fact, such kind of quantization ideas then can be widely applied to many different applications. One example we have is for the emerging devices. So we have been working on RM devices, especially early stage. The yield was low. The data representation is not very stable. So, multi-level representation, in fact, is not very reliable. So we propose a few methodologies in order to make like binary or quantized representations, and this is one of the schemes. So by observing different layers, actually the weight has in different distributions, and through training, we're trying to identify the corresponding weight parameters for 1 and 0s across different layers. And that leads to the further research at algorithm level is talking about, hey, why we observing the deep learning architectures, and clearly each layer has very different contributions to accuracy, to latency, to memory, and so on and so forth. So the goal, in fact, is to find or search for different precisions and for different layers. This is ideal, but in reality, if we really include it into neural architecture search structure, with so many combinations, the search space increase very fast. In addition, while we're talking about the sparsity levels and like precision level with the 2 bits and 4 bits, and this is a descript representation, which is, again, not suitable for the searching. So we took a back step and rethink about this. So one, can we reduce the precision representation for a fixed point quantization format? Okay. And here is an example over here, right? So again, if we remap and fixed point representations to like binary representations, and if all the elements and of MSB, most significant bits are zeros, in fact, then we can just reduce the hardware requirement directly. For the situation like the LSB is equals to 0 for odd elements, and then we can also reduce the use of a crossbar array, for instance, and the only change is to applying a scaling factor of 2. So while we're doing this, we kind of feel, hey, there's a chance for us to combine or unify the quantization and pruning techniques, the structure pruning techniques. So what we do, in fact, is we first perform an 8-bit quantization, which is pretty mature techniques for novel days. And very importantly, in the following, we convert such quantized model to bit-level representation. And then along the bit directions, we applying this in structure sparsification techniques, structure pruning techniques. And by doing this, we are able to convert a quantization problem to a pruning problem. And the search space actually is not tremendously large, and also it's kind of a continuous space optimization. Well, so far, my focus has been on single device, and when we're talking about this, and computation, memory, latency are the major things, and so we talk about the pruning techniques and quantization techniques. For edge computing, it's very important to think from top level, like a large set of the devices. And when we really consider many devices, the communication cost cannot be ignored. In fact, it becomes the new bottleneck. So we started this study through just the general distributed deep learning. The top one shows the parameter servers, and that holds the global model. And yearly, it's distributed the global models to different devices. Each device holds a fraction of an overall data set, training, and then submit updated models to the parameter servers and for aggregation, update, and then the model will be distributed back to each device. So in this case, as I said, and the communication becomes to the new bottleneck. So again, at that time, so we tend to apply quantization concept to distributed learning ideas. So our idea was instead of transfer the real weight, we actually can transfer the gradient. Number two, for the gradient, instead of transfer the raw data, then we may consider the distribution. And with these concepts, we are able to use 0, +1, and -1 to represent directions of the gradient. And with all these, we find that we are able to convert 32-bit floating point of the gradient into 3 bits. For each layer, in fact, we require a floating point scalar to represent the difference across layers, but still it's achieved much efficient gradient transfer. And in fact, the training performance was not degraded at all. Later on, we move our study to federated learning. Compared to distributed learning, federated learning have to handle some specific situation. For example, the devices could be very different. And for example, the training is asynchronized. And also, the data across different devices are collected by the device itself. And so we say each user has their own data. And generally speaking, these data represent non-independent and identically distributed way. So what we want for federated learning is each edge devices to train at local with their own data, so data do not have to be shared globally. In this way, then privacy can be preserved. And then later on, some people also thought about that, and can we personalize in each device model? So, it's optimized and based on my own device, my own data instead of others. So we did substantial work on here, and I only present one called Fat Mask. The goal here, of course, is to reduce communication, have personalized models on each devices, and also while we are doing this, and we're trying to simplify the models on each devices and make sure very efficient execution. So the key idea here is to train a binary mask instead of the whole model. So the information exchange, again, it simplifies to 0 and 1. So our structure, in fact, is to have a frozen model and distribute to the edge devices. And at the beginning, based on the local models, and we can do structure pruning. And then the trained mask will be exchanged with the global servers. And then we aggregate this binary mask across different devices and redistribute it. Okay. So again, in this way, since only binary data in transition, the communication can be tremendously reduced. So at the end, the trained mask will be element-wise and applied with the frozen models to obtain the local model for execution. So local model is only a subset of the overall large models. It's realized personalization. It's also reduced the computation cost. I don't show a lot of data over here, but here is our evaluation, one side of the evaluation. The red star represents our results. And for all the data set, x-axis is the inference accuracy, and the y-axis is the communication cost. And of course, the right bottom is the optimal point, and our method sits at the red bottom for all the cases. So one thing I wanted to point out is BNN fat average and binary neural network and the fat average is also used in binary data in transition. So the two methods have a similar communication cost, while our model has a much better accuracy. So very close to the end. In fact, when we're looking back to the past and like 10 years or so, we have been working on making AI models more efficient. And during this processes, we always keep in mind the importance of available hardware resources. And we propose clustering, pruning, quantization method, and tend to integrate with the hardware improvement as well. So normal days, model kind of grow large. So we've been working on some large language models and also large-scale systems. I wouldn't jump into details, and this is one example, like recommendation models. So while we're talking about the recommendation models in edge setups, in fact, there are two customers, the cloud server and also edge devices. So we collaborate with the Meta and talking about investing how to search or build more efficient recommended models at the cloud edge. And then we also study how can we personalize and apply to the edge devices. Similarly, for large language models, and people are quite interested in a mixture of experts that does enable the scaling a language model. However, the data path becomes very, very complicated. And then how can we optimize that? And this is the ongoing work that we are doing. So in conclusion, the entire research we have aims to efficiently deploy AI models on the edge. So far, I talk about how to minimize the storage computation cost. And of course, another thread is to innovate hardware and made it in favor of AI model execution. So what we feel like, and for the futures, the model will still continue to grow. And therefore, how can we realize those large model and the large systems will be important. But again, we do feel like a full stack optimization from application to device is essential. And that's our goal. So this is all I have, and thank you for your attention. And I'm open to questions. Thank you.
Thank you very much, Helen. So we are actually right at the end of this keynote session, but we have the Later with the Keynote Speakers session right now at 2 p.m. in the VIP room. Does anybody have one very quick question that they would like to ask? In that case, I would like to thank you once again.
Thanks, Ian.
And we have some things for you. So first of all, this is a CEDA luncheon keynote.
Sure.
So Miguel would like to present a certificate.
Oh, thank you, Miguel.
Thank you very much.
Thank you.
Thank you.
Yeah. Thank you. Thank you so much.
And Andy, as our general chair, also has a small gift from the local area, I believe.
From the local, so thank you very much also
Thank
on
you.
behalf of the DATE organization. So thank you very much for the keynote. And again, this is a local present.
Thank you so much. Yeah, very nice to meet you. Yeah.
Okay, so now I would very much like all of you to come along to the Later with the Keynote Speaker session so that we can engage in a discussion, in-depth discussion about the topics that Helen has raised in the VIP room right now. Thank you very much.
Thank you.